In continuation to our previous video for the design of FIR filter using windowing technique, this particular video is focusing more on the design of FIR filter for the bandpass filter. In the previous video, it was specifically for the low pass filter, and in this video, we will be looking for the design of FIR filter for bandpass case. Again, we will be taking help of one of the example and will be proceeding further. Design a sixth order linear phase bandpass filter using Hamming window, the filter having cutoff frequency of omega C1 equal to 1 radian and omega C2 equal to 2 radian. Find the filter coefficient. As in the previous case, very first step is to draw the characteristic of the filter based on the requirement of the given question. As the question is basically based on bandpass filter, so we have to look into the cutoff frequency of bandpass filter. As the cutoff frequency given in this particular question is in a digital frequency, and the lower frequency is 1 radian and the upper cutoff frequency is 2 radian. As we all know, in the case of FIR filter design, the frequency is to be taken in the form of digital frequency. And the range for the digital frequency is between -pi to pi. And we all can see here the cutoff frequency is given between the range of 1 and 2, between the range of 1 to 2 radian. And during this particular cutoff frequency, the magnitude characteristic of the filter is 1. And apart from these cutoff frequency, everywhere the magnitude information is 0. The same thing can be mathematically written as the HD omega, that is filter response, is given as 1 into e power minus j omega tau. As in previous case also, we have seen the tau is our delay, and the delay value depends on the filter coefficient -1 divided by 2. In this particular question, it is a sixth order filter, so the number of coefficients are defined as 7. And in that particular case, the number of delay, that is tau, equal to 3. So HD omega is equal to 1 into e power minus j omega tau, and it is between the range of omega C1 to omega C2. Modulus value of omega C represent the same frequency will be assigned to the left-hand side of the explain and the right-hand side of the explain too. As the given information is in the form of frequency domain, and the requirement in the given question is find the filter coefficient, that is in time domain Hn, and small n value will vary in this particular question is between 0 till 6, because the coefficient of the filter is 7, as the order given in this particular question is 6. So very first, again, we will be taking help of inverse Fourier transform, and we will be finding the HDN from the given value of HD omega. Using inverse Fourier transform formula, we will be reaching to the particular equation, that is simplified equation, is in the form of sine of omega C2 n minus tau minus sine of omega C1 n minus tau divided by pi n minus tau, where omega C2 given here is 2 radian, omega C1 given here is 1 radian, and the value of tau is here in this particular question is 3, as tau is equal to 7 minus 1 by 2, and small n is a variable which is varying between the range of 0 till 6. And this particular equation doesn't hold good if the small n value and the tau, that is delay, is equal. In that particular case, it is in the form of 0 by 0, and we have to look for L'Hospital rule, and we have to, according to that L'Hospital rule, the simplified form of HDN when n is equal to tau is in the form of omega C2 minus omega C1 divided by pi. So these two are the equation. The first one is when n is not equal to tau, and the second part is only when n equal to tau. As in this particular case, HDN is in the form of 0 by 0, and we have to use L'Hospital rule. The value of tau, as we mentioned, is given before. Tau is equal to m minus 1 by 2, where m is number of filter coefficient. For the sixth order filter, the number of coefficient is 7. 7 minus 1 by 2 equal to 3. So with this all information given, and we are looking for the filter coefficient Hn, which is nothing but a multiplication of Hdn into Wn, where Wn is our windowing equation in time domain, and the required window in this particular question is Hamming window. So before we move to the window, very first we have to look for the filter coefficient HDN, which is according to the equation sine of omega c 2 n minus alpha or tau minus sine of n minus omega c 1 n minus tau divided by pi n minus tau. So we will be varying the small n value from 0 till 6, and we'll be finding the filter coefficient HDN for all the values of small n between 0 to 6. While doing the calculation for this particular HD0 till HD6, we will be keeping the calc in the mode of radian, and same thing will be continuing for the case of window 2. So when we will be simplifying this equation, the value is coming as minus 0.043 for the value of HD0. Similarly, we'll be moving for HD1, and the equation becomes sine of omega C2, that is 2 into 1 minus tau, that is 3, minus sine of omega C1 n minus tau divided by pi n minus tau. After simplifying this particular equation, the value is coming as minus 0.265. Similarly, we'll be repeating this all the coefficient between 0 to 6, and we'll be seeing in the case of HD3, the equation doesn't hold good, and that time we will be following the equation of WC2 minus WC1 by pi, which is nothing but 2 minus 1 by 3.14. Once all the coefficient of HDN has come, we will be looking for now the Hamming window, and the standard form of Hamming window equation is Wn is equal to 0.54 minus 0.46 cos of 2n pi upon m minus 1. So very first case, we will be taking the equation when n is equal to 0, then in that particular case, W0 is equal to 0.54 minus 0.46 into cos of 0, which is nothing but equal to 0.08. The windowing equation for the small n value of 1, W1 equal to 0.54 minus 0.46 cos of 2n pi. Small n value is 1 now, divided by capital M minus 1. The value of capital M here is 7 as a filter coefficient length minus 1. So denominator throughout will be keeping as 6, and the numerator coefficient of cos function is 2 pi into n. As n is an integer value, we will be keep varying n from 0 till 6. So we will be looking here again the coefficient for windowing equation W1 is coming 0.31. Again, we will be keeping into the account the mode of calc, that is to be kept in the radian mode, and after that cos of 2 into 3.14. Cos of 2 into 3.14 by 6, or in a simple form cos of 2 pi by 6, which can be written as cos of pi by 3. Once we will be calculating this all the values of windowing equation from W0 to W6, we will be looking for the coefficient of Hn, which is nothing but Hn is equal to Hdn into Wn. And now we are ready with the coefficient of HDN for all the small value of all the values of small n, and the coefficient of Wn for all the values of small n. We'll be multiplying further, and we'll be seeing the type of symmetry it is following. As H0 is equal to HD0 into W0. HD0 we have calculated before, and we multiplied with the windowing equation W0 when n is equal to 0. The value is coming as 0.08. And after multiplying these two equations, we'll be reaching H0 as 0.00357. Similarly, we'll be looking for H1, H2, H3, H4, H5, H6. Once these all values will be coming, then we will be checking the symmetry of the particular coefficients. As we all can see, it is again following the symmetry property of FIR. The coefficient of H0 is same as coefficient of H6, and the coefficient of H1 is same as coefficient of H5. Coefficient of H2 is same as coefficient of H4, and H3 hold unpaired. So from here, it is saying the filter which is designed using the given information is symmetry and odd. So this way we can calculate the filter coefficient for bandpass filter for the given specification. I hope the video is useful. Thank you.